Hello and welcome to the NASA imaginAviation 2023 edition. My name is Uthman bin Affan, and I'm a materials research engineer at NASA Glenn Research Center. I will be your moderator for today's panel discussion on the building blocks of technology development. The technology building blocks from atoms, from fundamental research to production to testing and all the way to flights, all these pieces are needed to innovate new types of materials for aviation. This could be lightweight materials, this could be durable materials, high temperature materials, or functional materials, to name a few. Behind this technology, there are the key building blocks, which are the people and the teams involved to bring a product to flight, to benefit not just NASA, but the world. We have a sign here at the main gate that says research and technology for the benefit of all. Well, these materials and material research has been and still is a foundation of NASA and aeronautics. And while NASA works on many diverse materials, today we're going to focus on a special type of material, a very near and dear to me, known as shape memory alloy, or SMA for short. Shape memory alloys have been used in aviation since the 70s. In fact, some of the early adopters of shape memory alloys. And recently, these materials have been used in a major flight program, used in the form of a vortex generator, in collaboration with industry and government agency, etc. So what's the role of shape memory alloys? And what's the impact they can have for aviation today and moving into the future, which is the goal of this panel? So to help us provide some insight, we have assembled a dynamic powerhouse panelist to give us their views on this topic. With us, we have Ted Calkins from the Boeing Company. We have Terry Woods from the U.S. Food and Drug Administration, or FDA. We have Sierra Balkenbush from Fortune Metals. And we have Steve Arnold from NASA. Thank you all for being here today. So let's start the discussion with the aviation question. Tad, Boeing has been in the SMA technology for some time now, and you are currently leading several SMA projects too that will enable an improved aviation future, not just today, but also in the future. What can you tell us about SMA applications in the air industry in general, and how do you see the role of material development, which is the theme, or material research, in the current vortex generator project and future applications?
Yeah, thanks, Ivan, and good afternoon, everyone. So my name is Tad Calkins. I am from the Boeing Company. I'm out in Seattle. I'm part of Boeing Research and Technology, and I've been working with smart materials and smart structures for most of my career, and recently been very involved with the shape memory alloy work. So good question is what can shape memory alloys do in aerospace? And it turns out the unique actuation capability and the multifunctional properties of shape memory alloys give us some really interesting opportunities in aerospace. We've identified three kind of areas that we focused on. One has been replacement actuators. So this is where we take an SMA element and replace a current element. And the reason we do that is we might get better performance, might be lighter weight, have better reliability. So those kind of things. So we'd replace something that's currently on an airplane, for example, an actuator that moves a surface, a flap with an SMA element. We also can look at new capabilities. And this would include things like what I mentioned a minute ago, the vortex generator. So we have vortex generators on airplanes, but with a shape memory alloy actuation element, we can actually make those vortex generators move. So we can deploy and retract them. And this can actually provide some new capabilities to an airplane. Other examples of kind of new capabilities would be maybe a thermal management system. We might be able to use something like shape memory alloys to improve a heat exchanger, allow it to change properties, or for example, a satellite release mechanism. So we already have those type of mechanisms, but we can actually, and sometimes they're actually a element that has an explosive device. So getting rid of the explosive device and using an SMA element to create the satellite release mechanism can be very beneficial. And then finally, we can look at revolutionary applications. So when we have a new capability like a shape memory alloy actuator, it gives us some really interesting opportunities. We have different forms that the actuator can take. And this allows us to integrate it into a structure, for example, in different ways. And this gives us capabilities of doing things that we really can't do right now. An example of that would be morphing. This is something NASA's been interested in for years of, how can we make an airplane wing morph to different shapes and give us better performance? So with the shape memory alloys, we can actually integrate the actuators directly into the structure. And then, as I was mentioning before, that multifunctional capability, that SMA element can both be structural as well as an actuation element. It can also be sensing. It can also provide damping. So all those capabilities now can be incorporated into this wing, for example, and give us some really unique opportunities like the morphing. So examples of that include Boeing has done an engine outlet. So basically the nozzle of the engine, a jet engine, is able to morph and change shape to give you better performance of the engine throughout the airplane's flight regime. Another example is doing this sort of morphing with a supersonic airplane to reduce the boom associated with flying so fast. So these are all interesting opportunities. And then last point is, well, this all sounds great. Are these applications out there? Some of them are. We've been using things like hydraulic couplers for many, many years. But one of the things that's happened recently has been the very fast change in our material development capability. We can now do so many more things with materials that we just couldn't in the past. So now we're looking at the ability to design these shape memory alloy materials specifically for an application. And this is really quite exciting. It gives us the ability to have the perfect properties for a given application. And that makes these applications much more viable and much more better opportunities for us. What's improved here has been actually the ability of the medical industry to use shape memory alloy material and their commercialization, their ability to improve the material properties, reduce variability, improve processing techniques, has all created the opportunity now for us to take those same ideas, those same materials, and use them now in aerospace.
Thank you very much, Ted. And on the note of medical aspect, many of you know that shape memory alloys play a big role in the medical industry. And for that, we have with us Terry Woods from the FDA. So Terry, your team obviously have seen a lot of developments, a lot of up and downs in the SMA medical side since the beginning. So can you tell us how this prevalence and sophistication of shape memory alloys saves lives and enhances the quality of life? And given your experience from the FDA on the medical side, how would you summarize your number one lessons learned that you can provide to the aero community related to the widespread of SMAs as we grow and move forward with many more applications in the aeronautics?
Well, Nathan, thank you very much for inviting me. I'm sure a lot of people are wondering, why is somebody from the FDA here at this aviation conference? And I guess I'll give you a little bit of information about the FDA and then get into that. I guess at the FDA, I'm the chief engineer for standards and for strategic outreach. And the FDA's goal is to preserve, protect, and promote the public health. There are a lot of different centers in the FDA. There's about 18,000 people in FDA, and I'm actually from the Medical Device Center. That's about 10% of that, or about 2,000 people in the Medical Device Center. And what we do is try to make sure that patients have access to safe and effective, high-quality medical devices when they need them. And to do that, again, we regulate the medical device industry. There's about 183,000 different types of medical devices on the market, with about 20,000 device manufacturers and 25,000 facilities that we regulate. And in our device center, I spent almost 30 years in our engineering laboratories where we make sure that FDA is ready for emerging technologies when they show up in new devices, so that we know the right questions to ask and the right assessments to get people to do. Not long ago, I moved to our standards program, where we try to make sure that standards are ready for their regulatory purpose, again, in helping to get people those devices when they need them. Again, what does any of this have to do with nitinol? I feel like, nitinol was a material, that's the principal shape memory alloy that we see, developed back in the 60s. And it seems like it was a material looking for a purpose. And I think it was pretty perfect that in the mid 1990s, people realized that nitinol was a perfect material to use for a lot of different medical devices, in particular cardiovascular devices, places that you need a lot of deformation and something that's not going to corrode when you put it in the body. And so we started to see these developments in a lot of cardiovascular devices incorporating nitinol. About the same time, FDA was looking for a permanent home. We had been in rented buildings all over the DC suburbs, and the Base Closure Commission had closed the Naval Ordnance Lab just outside of Washington, DC, and they chose that for the home of FDA. And we still have the original Naval Ordnance Lab building is the head of our headquarters. And again, I thought it was just appropriate that FDA moved to the Naval Ordnance Lab, because the name of nitinol, nickel titanium, NOL, is the Naval Ordnance Lab. So we'd kind of come full circle. The material was developed there in the 60s, and then FDA and the Device Center in particular moved there in the late 90s, early 2000s. But the places that we mostly see see shape memory alloys in medical devices are places where you do have large deformations that you want to recover. And so most of the medical devices exploit the super elastic properties of shape memory alloys. Things like coronary stents or endovascular grafts, where you might have a big stent-like structure that you want to get into a person non-invasively. So you crunch it down into a catheter and insert it in your femoral artery and thread it up to your heart or to your aorta, and then you can expand it. And again, that's something you just can't do with conventional metals like stainless steel. And so nitinol, again, is the perfect material for those kind of applications. I guess another place that we see a lot of nitinol devices is in guide wires. Again, cases where you need to thread a device up through a tortuous pathway in your arteries or in your veins, and see lots of deformation, and have the device be a very small profile so it doesn't obstruct the blood flow, but able to, again, assume those tortuous shapes without fracturing. Outside the cardiovascular area, we also see a lot of nitinol devices in the dental arena, in orthopedics. If you have kids, you've likely had they've had braces that had nitinol wires in them. Mm-hmm. The taking my kids to the dentists, it's like always, can I take the samples home? Can we play with them, bring them back to the lab and play with them? And, the dentists roll their eyes, but they're pretty good sport and hand over, the extra nitinol wires that nerdy mom can take back and look at in the lab. But I guess, again, thinking about nitinol devices, that we see a lot of laser cut tubing, and we see a lot of nitinol wire. And the one, I guess, question that the response that we give to people when they ask us about, how do I assess my nitinol device? The answer is nitinol is not nitinol is not nitinol. It's all completely material processing dependent and dependent on the, on the history of deformation. And I guess that, kind of leads us into talking to the Sierra, who's the expert in manufacturing and processing, and, how do you treat this wacky material to get it to do what you need it to do in all of these applications.
Great question, great answer, Terry. Thank you very much. And leading to what I see a parallel and very similar path. The medical industry went through the manufacturing saga of making things perfect, very critical for the human body to obviously lives in stakes here. And I see the same for aeronautics. And you have a plane full of people, so your devices need to function the way you intended. And manufacturing comes into that question. So with us here, Sierra Balkenbush from Fort Wayne Metals, on this topic of manufacturing, can you tell us about the challenges and perhaps those challenges turn into opportunities in the manufacturing of shape memory alloys? And how important it is, something that we don't talk about a lot, how important it is to have a user or a regulator in the loop to sort of provide that feedback while you manufacture these materials for a given application in aeronautics, for instance.
Of course, thanks, Atman. Hi, I'm Sierra Balkenbush, as he said, and I'm the program manager at Fort Wayne Metals for nitinol actuators. I've been in the nitinol field for about 10 years now, and the first part of my life, as Terry discussed, was medical. So I got to enjoy that super elastic side, where the material was transforming below body temperature. And now we're on the flip side where we're working on the material transforming above body temperature, which is, as we typically call SMA versus super elastic here. Atman also mentioned that, this has been used for, since the 70s. And, now we're at this point where we're making medical nitinol all the time and people are comfortable with it. We have those standards. We have, places to go and be able to get those resources for how to use it, and people are comfortable. Whereas, in this last 5 years that I've been involved, which this group has been involved for a long time as well, we're really working on taking that next step and being able to use SMA in applications, whether it's aviation, aerospace, or anything where the material is needed to transform higher. As Terry also mentioned, the manufacturing side of it. We make material all the way from melt down to wire. And it's not just that final step where, everything becomes an actuator. We make an actuator element that goes into these applications, a vortex generator or switches, anything that you can think of, because it's lighter, it's smaller, it's quiet. But one of the biggest challenges that we have is that there aren't standards necessarily, and we're all making actuators differently, so to speak, with all of the different people making them. So to answer your question, Atman, about having a regulator involved or somebody to give you that feedback, there's a lot of properties in the material that start from the time that you start manufacturing it, drawing, annealing it, making it to where it's good for functional fatigue or performance. Everyone's doing it a little bit differently, and we just don't have those standards out there yet in which everybody's making the same. So you're very, very closely working with, did I go off? We're very closely working with the customer and how to integrate this actuator element into the actuator itself. Sorry, everybody froze for a second. Are we good?
Yep.
Yep, awesome. And so that, I guess that would be one of the biggest opportunities that we have as we go forward, is building that knowledge and building those standards and getting the whole community comfortable using the material, talking the same language, and getting all of that stuff out there to where it's easily accessible, so that we can all pull from the same things and be able to integrate the material much quicker into the applications.
Thank you very much, Sierra. And for those of us listening to us online, we had a small delay in the transmission, so hopefully you got most of Sierra's answer there. So continuing with the theme, we had a panel yesterday stressing the importance of data management and aviation, etc., and data and all. But here, in the sense of SMA, when it comes to data and databases in general, it's a big word when it comes to shape memory alloys, almost non-existent to some extent. And someone that knows about this data in general, data management, is our own Steve Arnold from NASA. So Steve, I'll ask you the question. NASA efforts in this area over the years hasn't been minimal. There are so many works going around databases, data management, proper data storage, etc. So how are the efforts under your program, under TCube, enable better data management? And that's in the area of, could be gathering, analyzing, synthesizing, etc. What could be also for model input, so for material research or discovery. So what can you tell us about the world of shape memory and the data management aspect of it?
Thanks, Amin. Yeah, I'm Steve Arnold from NASA Glenn Research Center, and I'm the Materials and Structures Discipline Lead for the TTT project. So yes, Amin, as a consumer of the data, because we're interested in modeling and so forth, I'm very interested in material data information management and have participated in it for probably about the last 20 years or so. And as such, within the TTT project, we have stood up a focused area actually this year to really enhance that whole concept. And we've entitled it Materials Informatics, and that's concerned with developing the necessary infrastructure to enable efficient, robust material discovery and innovation. In the case of shape memory alloys, the TTT project released last April a unique publicly accessible database and tool set with over 1.5 million data points, which really enables fast and efficient, accurate design of SMAs and should promote community-wide expansion of these types of materials. And as you well know, Atman, due to the existence of this database, your team was able to design and field 2 new SMA materials tailored specifically for use as torque actuators for deploying and storing vortex generators, as Tad had spoke about on the Boeing Eco Demonstrator flight test, which really was, quite a feat, because it's typically takes, historically, right, new materials have taken about 20 years to come to fruition from, concept to implementation. And you guys actually did that in I think it was about a year. So that was really pretty incredible. Additionally, for materials kind of just in general, like you said, we have to store all sorts of kinds of data and metadata. That's data about the data. And that data can be real, which is experimental data, or it can actually be virtual or simulation data. And we're really trying hard to connect those two together. And so all that has to be addressed in our digital thread infrastructure. And that type of data, it's actual, values, point-wise values. It can be logical data. It can be short or long text. It can be images like micrographs, PDF, functional data, chemical compositions, and so on. And actually, I'm going to share a lot more details about this and how we're integrating our machine learning and artificial intelligence into our data ecosystem during GatherTown later today from 3 to 4:30. And the name of our poster booth is Materials Informatics Enables Rapid Material Discovery. So I hope everybody would come and check us out. And, and then, you as you said, and people haven't really been, people have always wanted data, but we've kind of personalized it. And so we're really trying to develop a digital culture now within NASA, where we're trying, at least in the materials area, we're trying to capture the entire material life cycle. And that involves, like you said, capturing the data. Then we have to be able to analyze it. We have to be able to maintain it, and we have to be able to disseminate it. And we have to do all that in such a way that both researchers and designers can get the right information at the right time in the right format, so that we can accelerate the material discovery and innovation. And so really, I guess as a last point, I'd like to just say out to anybody who's thinking about doing these kind of things, it's really important that, data is key, obviously, for developing both physics-based models and data-driven models. And so we really have to be concerned about capturing this data and maintaining it and so forth. And we need to do that at the beginning of projects, and not just as an afterthought at the end of projects, and which is really the way it's kind of done today. And so again, we're really working hard to build the data ecosystem, the digital ecosystem to handle all of that, so that we can capture and maintain and disseminate the information that we so desperately need to advance material discovery and innovation. So, thanks.
All right. Excellent. Thank you all for your answers here. And now we will move to Q&A sections of the program here. To start off, as the questions trickle here, to start off, there's a combined question for both Ted and Sierra. Steve just mentioned capturing data, but there is some interest in before that capturing the material, as Boeing works on developing these actuators and devices, working with government agency, for example, like NASA and others. How is that material being scaled from an industry perspective? Is the industry looking at scaling a material, if it nitinol is great, if some other form, maybe for high temperature or low temperature, to sort of supply the application when the call comes in, we need thousands of these devices?
You want to start, Sierra? Oh, I can't hear you.
I'm good now. Sorry. Yeah, I certainly can. To your point, Ahmed, when that request comes in first, and we're working, with it, NASA or Boeing or whomever that customer may be, the first thing is, of course, understanding what it is that they need, because at this point, everything is very, it seems very custom, right? Very much to that application, being able to work on that. So once we get that and we start to get a product that works for those specific requirements, from that point on, it's very individualized at this point, how we scale that up and hand it over. It takes very close collaboration between us and you guys, is not only from just making the material, but what type of testing and what type of reports you guys are looking for.
Yeah, and just to add on to that, Terry was mentioning the work that the FDA does with the medical devices. Similar standards are being developed for the high temperature materials that we talked about earlier, the ones that provide actuation. And as we develop those same sort of standards, again, that are available now with the medical industry, it does provide, I think, an easier path for us to see the materials be developed, commercialized, and then made available on a commercial basis. And one of the things, aerospace applications have in general been kind of low volume. You think about how many satellites you put up, that sort of thing. It's not like a consumer product. So in a lot of cases, I think the material will benefit from, or the availability of the material will benefit from a wider range of applications in different industries, and that's when, in aerospace, it'll kind of be able to graft off that. So a lot of great opportunity, though, in a lot of industries when you look at the shape memory alloy world. For example, automotive industry, there's actually a lot going on. It's really, really quite exciting.
Excellent, thank you. And this next question is for Terry. The medical industry has been doing this for a while now, and so much data has been generated at some point. So the question is, where is that data? Is that data available somewhere for nitinol, or perhaps some derivatives of nitinol that people can use and learn from for aeronautics developments?
Well, I guess that's a great question. As far as the data that companies use to submit to the FDA for specific applications is proprietary, and so we can't share that. But one of the major functions at the FDA labs is to generate information and data that's shared with everyone. For instance, we have a lab program going on right now looking at high cycle fatigue data for nitinol wire. Your heart beats about 300 million times in 10 years. And that's the level of evidence that we want manufacturers to submit. But the question is, what happens, beyond 300 million up into the billions of cycles for nitinol? And again, we've been working on a project to generate this high cycle fatigue data, which we will share, freely. The FDA labs output is supposed to help all industry, provide information to them to develop their products. It was interesting to hear the talks about, what format do you actually put that data in? you need to think about it as you're designing your experiment so that you have your data somewhere that can easily be used. So I think, maybe that's a place that we could collaborate with NASA about, using those mechanisms for sharing the data with the rest of the community.
Okay. Steve, you are on mute if you're answering.
Hey, Terry. I was just thinking, are you familiar with the ASM's medical device database?
Yes, that's a fantastic database where I guess experts have mined FDA applications for publicly available materials data, which again, it's a great place for people to go to get a lot of data from those ASM
Right.
databases. So yes, I'm definitely familiar with that.
Yeah, we have a lot of Ottman and myself are pretty involved in ASM, and we have a lot of collaboration with them, and so that could be a great way for us to interact is through that.
Excellent. Thank you. This next question is for you, Tad, and it goes like this. How does the addition of new SMA components in aircraft impact their certification timeline?
That's the $1 million question, maybe even more than $1 million. So anytime we have a new technology that we're going to put on a commercial airplane, for example, we do have to figure out, how are we going to certify it? So just as Terry was talking about with medical devices, there is a rigorous process that's going to have to take place to make sure that this new element, new material is going to meet all of our requirements. And the FAA has requirements on exactly what materials have to do, how they have to respond. And the question or the discussion earlier about doing the life cycle testing, that's going to be a big part of that database that has to be developed on the material and then shared with the FAA as part of the certification process. So the question of what does that add in terms of kind of a process or a time. So we'll take airplanes, for example. With a new airplane, we could put a new SMA actuator on, and the testing that's associated with a new airplane would essentially prove that this SMA element is going to be acceptable, right? And as we go through the rest of the certification process with the airplane, that SMA element would be certified. When we look at other types of implementation, though, maybe you want to change something out, a replacement actuator, for example. So we already have one now. We're going to replace it with an SMA actuator. This provides a really a different process. And we would have to go back then and really look at the properties of kind of this new actuation element and the new materials involved and compare it to, the previous currently available system. And so the end result is, there's definitely a cost. And hopefully the business case matches, though, in the sense that the value that comes out of providing something new is worth the cost of implementing it.
Thank you very much, Ted. Our next question from the audience here for Sierra. Are these materials recyclable or reusable in some way?
That's a great question. They currently are not recycled just because I would say the cleanliness and the careful part, or the care that has to go into melting these is so critical in the performance. As far as reusable, though, if we're talking, in fatigue or cycle life, they last for a long time. Some people can remelt them into nitinol, but we're talking, as most of you know, 1%, can change what grade of material this is. So none of the main manufacturers will recycle these materials. But they're cleaner than a lot of the standard things that, they would be replacing as far as actuators themselves.
I understand. I'm aware of some costly alloys like nickel, titanium, platinum, and palladiums.
Very much
20
so.
or 30% weight percent, and those are very much in need of recycling to reclaim that precious metal.
There are some that we will do that with, yes, without doubt.
Excellent. So, Steve, this question is for you. So when developing databases, An audience member said, how do we balance NASA's responsibilities to make data available with industry while keeping the effort to protect the IP?
Well, we're required to maintain the IP, and so we've built our systems with the opportunity to have a access control, and so we know who is trying to view the data, and then we know whether or not we can release that data to them. So if it's proprietary or whatever, you would have to either be a government employee or be an employee of the company or whatever who has the rights to the data. So we are very concerned about that, and you're right. There is a balancing there. We've actually adopted in our material management system, we use Granta, and they have two options. They have a record, or they have what they call an attribute based. We've done it as an attribute based. It's harder to maintain, but what it does is it allows you to open up as much data as possible. So in other words, if there would happen to be one data item on the record that was ITAR'd or something like that, most systems would just shut down the entire record. We will actually only hide that one value then from a person or whatever who might not be able to see ITAR, but they'd be able to see everything else. So we have taken a strategy to maximize our dissemination, you might say, of information to the public, since that's our primary motive is for the betterment of all. So we do try to take that into account, and yet we are very conscious that we have to protect people's IP.
Can I jump in here?
Go ahead, Ted.
Just to be clear, though, NASA does license their technology, including materials like the shape memory alloys. And in fact, that's how Boeing was able to use this unique alloy for the deployable vortex generator flight test. So there really is a good path forward. And I think there's very good coordination between what NASA does developing something new, and then industry's ability to use these new technologies. And then obviously with the goal of going off and trying to commercialize a product down the road.
Yeah, absolutely. And just to add to that, a lot of data is public, is out there. The challenge is to put it in front of you in one shot, in one place. In addition to the data that is with customers with IP that cannot be shared publicly, but there is so much data that is public, and only having it in some place that you can look at it, learn from it, discover, use it, that's by itself is very beneficial.
Right, and that was the whole point of of your development of the SMA database, so that it is available to the public. It's taking all the reference data, putting it in one place, and allowing people to manipulate it, see it, and so forth. So yeah, that's a real public service, into the community, actually. Yeah.
All
That's
right.
right.
And in the short minute that we have left, I have one quick question, perhaps to Terry and Tad, about standardization standards. Like, what are the actuators regulated for materials regulated for actuation compared to, for example, other applications could be medical standards or automobile standards, etc.
Well, I guess as far as the material standards, I work a lot in ASTM and in ISO developing standards for both test methods and for specifications. And if the range of properties that you're looking for is similar, then I think you could use those you could use those standards for applications beyond the medical industry. Although I'm not sure that the materials are similar enough that you could really use them. I don't know, Tad, if you have anything else to add about standards.
I can jump in there too, if you'd like, being on both sides of it. A lot of the standards we do use the same, whether it's chemistry or the cleanliness. A lot of the test methods are used in like processing controls, bringing it down, but that does not give us final performance. Tad and his group at Boeing, and some of you were involved, I'm sure, as far as the function of the material, ASTM E3097, E3098, that work is going on. But we're taking a lot of it and taking it to that next step to be able to take that material and put it in the application.
All right. with that, we would like to end it here. I would like to thank you very much all for your valuable contributions.